Yes, ma'am.
Yes,
Yes.
ma'am.
Okay. So this capacitance of a single core cable, whenever we are dealing with underground cables, we know that it can behave as a capacitance. How? The inner portion or the inner diameter will behave as one of the plates of the capacitor, and the outer diameter will behave as another plate of the capacitor. So how it will work? The inner ones, which is actually the core or the conductor part. Okay, so the core or conductor part forms one of the plates, and the outer part of the conductor, which is the insulation, rather the outermost, we can say as sheath. Then this sheath and the conductor acting as two parallel capacitor plates. So two plates of capacitor, just two plates you consider, just like that it behaves. So how will we address this? The conductor, which is the core part, that is actually the current carrying, charge carrying thing. And the sheath, that is actually our one which is at the earth potential or earthing or grounded, it is that portion is done. So we will consider it like that. If we are to calculate the capacitance of such an underground cable, then how will we proceed? For calculating capacitance, we know that capacitance C is equals to, means capacitance C is equals to Q by V, where Q is the charge and V is the voltage. Okay, so we will calculate Q, we will calculate V, and then we will calculate the capacitance, which is C equals to Q divided by V. So starting with this part, this is a single core cable, and its cross sectional view is shown in this side. So it can be drawn like this, that concentric circles are there. Our main concern is to find the capacitance at a certain random point P. You see the point P. If we are told or if we are asked to find the capacitance at that point P, we will take that that point P is, or that point P has a small portion of elementary length of dx. Okay, you see dx, the small elementary length of P, or rather the elementary diameter of, we can say, although it's a very small point, it has a certain diameter. So that point we are taking as a length of dx. Okay, and the inner core diameter or the conductor radius is small r, and the outer verge radius is capital R. So taking x as the distance of the point P from the center as x, we are now calculating the first part. So this is a single core cable which can be drawn like this, coaxial cylinders, we can say, where the inner cylinder is the conductor and the outer cylinder is the lead sheath, which is at earth potential. So let us consider, if this small r is our radius of the inner core and capital R is the radius of the outer core, then let small d be the conductor diameter or the core diameter, diameter of the core, and capital D be the total diameter of the sheath. Just like this. If small r and capital R are the radiuses, then small d and capital D are the diameters. Now you take Q as the charge per unit length. Okay, Q is the charge per unit length, and permittivity is represented by the symbol. Okay, so permittivity of the material between the core and the sheet means inner diameter and outer diameter. Between that, the permittivity, the material that it has, its permittivity is given by this sign. Okay, so epsilon is this, and epsilon naught and epsilon r, the symbol of permittivity, is the our product of these two is the total permittivity of the material. So epsilon naught is the permeability of free space, which has a certain value, and epsilon r is the relative permittivity of the medium. So we can have that epsilon equals to epsilon naught and epsilon r, the product of these two will give the permittivity of the material. Now, considering all these things, that the elementary cylinder with radius x, yes, this cylinder with radius x, because the point P has a distance of x from the center. So the elementary cylinder with a radius of x and axial length of 1 meter. Just remember this, the axial length of that elementary cylinder is 1 meter. Okay, so the thickness of the cylinder is dx, because we are taking the thickness part as dx. Now, this is totally as per Gauss's theorem, that the lines of flux that comes out, okay, due to a charge q on the conductor are in radial direction, means outwards direction from this. Outwards direction. Radial means from the center to outwards. Okay, so if it is radial in nature, radial direction, and the total flux lines are equal to the charge possessed, that is q lines, then as the lines are radial direction and the cross-sectional area through the lines pass in surface area, then for a cylinder with a radius x, the surface area is 2 pi x into axial length. Okay, so this is a very known thing, that the surface area is 2 pi x into axial length. Now this axial length we have considered 1 meter for this elementary. You see, here this axial length is considered as 1 meter. So 1 meter, if I put the value here, 1, 2 pi x into 1. Here, 2 pi x into 1, if I put, then it will be 2 pi x only. So 2 pi x meter square is our surface area. So charge by surface area is our flux density. So flux density will be equals to q divided by surface area, that is charge divided by surface area, which is nothing but q divided by 2 pi x. Now, why I am doing this flux density? Because I want to have the electric field intensity at a point P. So the electric field intensity at any point P on the elementary cylinder is given by Gx. So field is given by G. Okay. So do not get confused. Electric field intensity is Gx equals to dx by epsilon, where dx is what? Dx is electric flux density. We just found out electric flux density, that is q divided by epsilon naught into q by x. So putting the value of dx, that is q divided by 2 pi x, we now put divided by epsilon. Okay, so dx's value is q by 2 pi x divided by epsilon, means divided by 1 by epsilon naught epsilon r, as far as this equation is concerned. We are just putting this value here in this equation. So q's value is dx's value is q by 2 pi x, and epsilon equals to epsilon naught into epsilon r. Now, what we need is the work done. So the work done in moving a unit charge through a distance dx in the direction of the electric field is gx into dx. So this is the work done. Obviously, because potential multiplied by, means if we want to have the potential, the work done, that is gx, field intensity, multiplied by the distance it has traveled, dx. So gx into dx gives our potential or the work done. Potential itself means the ability to do that work. So obviously, that is what? If the work done in moving a charge is nothing but the voltage, because potential means actually the voltage. So, therefore, the work done in moving a unit charge from the conductor to the sheath in the potential difference between the conductor and the sheath is given by this. So, obviously, we found a small portion of gx dx. So, the entire part we will find how? We will find by integrating. So, integration of gx dx within small d by 2 and in the upper limit capital D by 2. So upper limit and lower limit of gx dx, we will take the integration and we are getting this value. Okay, so V, the voltage part we are getting. Now, if voltage part is this value, obviously the capacitance is Q by V. So Q divided by V, we are putting the value of Q, whatever we got, and we are putting the value of V. Actually, we are keeping Q as it is, and then we will put the value. So finally, it comes something like this. But you have to note that the length considered is 1 meter, that is the axial length. Now, if the capacitance is farad per meter, considering it as 1 meter. Now, if it is required for a certain length L, suppose 5 meter or 10 meter, then multiply that C by L. Then you will get the value of capacitance. I hope this is clear to everyone. This is actually, I explained it twice. That is why you understood it, na?
Understood, ma'am.
Anyone has any question? Yes. Okay, very good, very good. So I'm just moving on to the next one, which is charging current. This is again something important with respect to, it's not that it will come in the exam or something, but charging current, how can I say? You can see the charging current, this term, particular term, charging current, you will see in transmission lines also. So, what is basically charging current? Whenever you are considering a cable or a transmission line, it will have some, it is actually basically capacitance. Means just like cables, I told you there is inner diameter, outer diameter, it is acting as a capacitor. In the same way, transmission lines are also acting as capacitor. So whenever something long for a huge amount of distance is acting as capacitor, then there will be always presence of charging current. Why? Because the capacitor stores a certain amount of charge. Now, whenever it is storing charge, it is having the charging current within it. So, this is the charging current which you will observe both in underground cables and in overhead transmission lines. That we will go on to later for the transmission lines. Now, this charging current is when the capacitance C of a cable is known, then its reactance is given by XC, that is 1 by omega C, obviously. If capacitance is there, there will be capacitive reactance. So this is the capacitive reactance XC. Now XC is equals to 1 by omega C. And we can write omega C as 2 pi FC because omega is equals to 2 pi F. Okay, so 1 by omega C equals to 1 by 2 pi FC. Okay, so this is capacitive reactance. Now, whenever there is, as I told you, the charging current of the cable can be given by I equals to VPH by XC, where VPH is what? Phase voltage. That is phase voltage between the core and the sheath, the two layers of capacitance and the two capacitor plates. Okay, so between the capacitor plates, whatever the voltage exists, that is VPH. VPH actually is 1 by root 3 times the line voltage. So VPH divided by XC is our charging current. Okay, remember this because this will be required later. Okay, next is the stress in insulation. You see, whenever insulation is there, there will be stress in insulation because the core is carrying a huge amount of current, and there will be leakage current due to the what can I say? The as the core carries the current, there will be leakage current anyways. However strong insulation you make, there will be some amount of current flowing. So obviously, there is this very huge amount of stress within the insulation part. It has to protect, and current anyway leakage is happening. So how will it protect? The insulation layer has this huge amount of stress. Okay, so that stress is this. There is a small derivation part, not a very big one of tough one. So stress in insulation is the electric field intensity acting at any point P in the insulation. You saw that point P just before. So in that point P, whatever the electric field intensity is acting, that is our stress in insulation. Now, Gx is equals to electrical stress at point P. Gx, as we told that field intensity or the field intensity only is electrical stress. Okay, so Gx is the electrical stress at the point P at a distance x equals to q divided by 2 pi, whatever the value it was. Now, V equals to q by 2 pi epsilon naught epsilon r. This value also we just got by integration, right? So integrated value, this v equals to this value, and q is equals to the value just 2 pi epsilon naught epsilon r v by ln d by d. Now substituting gx, okay, gx to be this value, now gx becomes this. Gx equals to v divided by x ln d by d. X ln d by d, that just you got from the v portion only. You have got, see, you have got v, you have got q. Okay, now as you have got v and q, you will get gx. How? Okay, how that is because the relation in integration you will understand with this. You see, this value was there. V is integration of gx dx. Now in v equals to gx dx, you are putting the value of gx, which was what? Which was this value, q by 2 pi into epsilon. So gx value is q by 2 pi epsilon. Now this only you are getting here. Okay, so as you see that this value is put here, now we are simply doing one thing. If anyone is not understanding this, just tell me. Q equals to this value, whatever the value you seek, 2 pi epsilon naught epsilon r v divided by ln d by d. This value you are putting in this left side equation of v equals to q by 2 pi epsilon naught this value. So v is coming in terms of this q equals to that term. So that you are putting here and you are getting the value of gx. Now this gx, the stress is maximum at the surface of the conductor, that is when x is equals to r. Obviously the stress will be maximum at the surface of the conductor, that is the innermost part of the core. Anywhere in the core if you proceed, then there only the stress is becoming maximum because the electric field intensity is more there. So this is maximum there. So g max, which is the stress, electrical stress maximum electrical stress, that is highest at the surface of the conductor. Now this value divided by the normal value will give you, or the minimum value rather, which is at the sheath, this at the sheath value and the maximum value, the ratio of these two, is the variation of the stress in the dielectric material. So this is the, you see the picture, then you will understand. The innermost part is the core part, so there you will get g max, and the outermost part is the sheath part. So in the sheath part, the electric intensity is G min. So the ratio of G max to G min, that will be your ratio of the two stresses or the variation of stresses in the dielectric material. So this one again, why needed? For the problems. It's not that this derivation comes. No, but for the problems, the formulas may be needed. Okay, so I'll just move to the next very small part, which is the economical core diameter. Okay, in practice, the maximum stress value should be as low as possible when the voltage V and the sheath diameter D are fixed. The only parameter to be selected is the core diameter D, small d. So small d should be selected for which G max value is minimum. Now the value of G max will be minimum when, again, maximum minima condition, G delta of G max divided by delta of D equals to 0. Whenever you are to determine any maxima or minima cases, you'll have to provide the differential of that equals to 0. So this you are getting G max's value, just we determine the G max value, that value only you are derivating. And after derivation, you are equating it with 0. That is, delta G max divided by delta D is equals to the derivation of this G max 2V divided by D by ln D by D. Now you are differentiating it, and after differentiating it, you are equating with 0, and you are having this condition that the value of delta G max divided by delta D must be 0 to get the minimum of G max. So small d is coming as equal to capital D divided by 2.718. So this is the condition of economical core diameter. Again, this is going to be the formula for the problems of economic diameter. So remember the formula. It is the condition that small d is equals to capital D divided by 2.718 if we have the minimum value of Gmax. Okay, if we want to get the minimum value of Gmax. So this is our condition. Now let me just look onto a simple problem regarding this. This is the simplest problem and often comes also. You'll see this problem, I think, in the question bank. Similar kind. So let's just read first. Find the most economical diameter. Find the most economical diameter of a single core cable to be used on 66 kV three-phase system if the peak permissible stress is not to exceed 50 kV per centimeter. Also find the overall diameter. So this is it. V line equals to 66 kV, G max equals to 50 kV. So you know the line voltage, you know the maximum value, because it has told that it should not, permissible stress should not exceed 50 kV. So it should not exceed 50 kV means what? Means the maximum value is given. So maximum value of G max is given. V line voltage is also given. Now you have to find phase voltage just by dividing the line voltage divided by root 2. You'll get the phase voltage. Now, when you get V for the most economical size of conductor, G max equals to 2 capital V by D. Note that the peak value of stress is given, and we are also using peak value of the voltage. So this is our equation. We are equating both sides and we are getting small d equals to this value. Now same thing, 2.718 we just saw. So that small d equals to capital D divided by 2.718. You are getting the capital D, which is the overall diameter, and the economical diameter you are getting from the small d equation. So the question has both parts, economical diameter and the overall diameter, both. So it will ask you the economic diameter. You go to this part. for economical diameter, G max equals to 2V by D. And if they ask the overall diameter, just go to this condition, small d equals to capital D divided by 2.718. So this is it. Once you find small d, you will be able to find capital D. Okay. So the two diameters are the questions that come for the problems regarding our economic diameters. So this is it. I'll leave it here. 12:30 already it is.